A Birkhoff billiard is a C1 closed regular curve in the plane. We can describe this also in the complex plane, which is the same. And here is a nice solution of the Frenet problem. If you are given the curvature, which is positive, or the radius of curvature is defined everywhere, then you have a positive, so you have a curve, and this is the explicit expression for this curve given the rho. And as long as this integral from 0 to 2 pi is equal to 0, then you have a closed curve. This is a cool way to parameterize. It's not arc length parameterization. It's the parameterization is actually just you take this as your t, this angle. So it's kind of a polar description. For every t you give the complex number, and then everything is very nice. You have the curvature explicitly given. You can also give the evolute, right? You just turn by 90 degrees and you go with the distance rho of t, and then you get to the evolute, which is cool. So there are lots of open problems about Birkhoff billiards. So you play the Birkhoff billiard here, so bouncing around a light ray or ball in that table, and you want to understand what happens. And this has been initiated here at Harvard in the 20s by George Birkhoff, and a postdoc of him, Poritsky, was working on this also at that time. He then kind of later, after Birkhoff's death, published a paper about it in 1950 and asked, for example, whether integrable billiard necessarily has to be an ellipse. Integrability has many different definitions, but you can kind of, one of the definitions is that you have invariant curves for the dynamics for every rotation number. Also, vexing is the Sinai problem. There's no such table known where you have a positive entropy. I mean, for large differentiability C3 or more, then what you have is invariant curves close to the boundary. And then also in general, what you have is periodic points which are elliptic, and so have invariant curves by the KM theorem. And so you have to deal with a mixture of stable and unstable motion in the same picture, and that's just mathematically we don't know how to handle this. There is also kind of a problem which is maybe not so much related to billiards. It is, because periodic orbits are related with the Dirichlet spectrum of the Laplacian. So you have here also a beautiful problem of Gilmer. The question is, if you have two tables which have the same billiard dynamics up to conjugation, are they also congruent tables? And I asked once whether there is a billiard with algebraic return map, which is not an ellipse. So I was actually searching for that. And one way to search for it, you have to kind of have a space to work with. One of the frameworks you can do is you can use harmonic analysis to define functions which are differentiable from any scale, CR. And that's the definition. You just look at the Fourier coefficients of this periodic function and look at how this decays. These are actually Hilbert spaces, Sobolev spaces, nice Hilbert spaces with an inner product, and so you can work with that. And then you have also subspaces where you have really, I mean, this is complex, but you have also subspaces where you have real tables. Like if A minus K is AK bar, this is not a complex subspace, but it's a linear subspace. And then you can also, you want to have closeness, which means A1 is equal to 0. That's this condition here. And then you want also maybe curves of constant width. That's what I was working on in 98. Curves of constant width are very, very beautiful. There are many of them. I mean, there's a Hilbert space of them. And here I printed yesterday one, and actually I just rotated it around, have a surface of revolution. Isn't that beautiful? That's 3D printed, and it's also related to the evolute. So what you can do is you can take the table and you let the wavefront go in. So if you let the wave go in, what happens is this caustic, or this evolute, is the place where the waves are concentrated, where the beams are focused, right? For a circle, it beams in the beams are focused in the center, and so you do that for every point. You look where it is focusing, and that is called the caustic or evolute. And in the billiard case, in this case, when you have a curve of constant width, what happens is then when you take a when you start perpendicularly, you end perpendicularly, right? Because what actually happens here, that's pretty cool. What actually happens is you have the same, you can actually do that. You have the same, this ball. It's not a ball, but it's a surface which has the property that it has everywhere the same width. So this means you can actually put it like a Kugellager. You can put it in between two plates and move the plates, and it doesn't doesn't change the height of the plates. Very nice surfaces. You can also, I played in that paper also billiards in that table, so 3D billiards, which is also an interesting thing. And then here you see something like the line of striction. The striction curve is the place where this kind of starts, where this folds up. All this is a ruled surface. It consists of lines, right? It's made of lines, one parameter family of lines, and this striction line is of interest for geometers. So it's quite a rich topic in differential geometry, and essentially covers what we did in 136, and it is Frenet's theorem. Explicitly, you get from the curvature, you get the curve, and you can study the billiard in that curve, and you can study the caustic. So what I did, what is the purpose here, is actually kind of explore examples, examples of billiards. But what you can do is you take regularity, the regularity kind of, you vary the regularity, you can get fractal, doesn't know whether it's fractal, the cost of dimension cannot be computed, but nowhere differentiable caustics. They have been later called hedgehogs. So a hedgehog, it's kind of a caustic which is nowhere differentiable. It's a pretty cool topic then also with relation with harmonic analysis or fractals, and so there are lots of open questions here. That's it for today.